Welcome back to the deep dive. We're about to plunge into some really fascinating source material today. It uses these tiny, buzzing creatures, honeybees, to reveal some pretty big, complex secrets about our cities.
That's right. We've got this unique research paper here. It basically enlisted honeybees and their honey as biomonitors.
Biomonitors, okay.
Yeah, and they used them to measure atmospheric metal pollution, specifically in two big cities, Brussels and Vancouver, during that really distinct period, the COVID-19 restrictions.
Ah, the anthropause. Yeah, feels like ages ago now, but scientifically, what an incredible, completely unplanned global experiment, hasn't it?
Absolutely.
So our mission today is to really take you through this specific study. We want to unpack what these amazing little environmental samplers, the bees, can tell us about how cities responded, geochemically.
And different cities too, right? Different structures, different histories.
Exactly. How did they react when human activity just, changed so dramatically, so suddenly? Think of it like a shortcut, maybe, to understanding urban pollution dynamics, all through the eyes of a bee.
Yeah, it's a great way to put it. So maybe let's start by getting a handle on this whole biomonitoring concept.
Good idea.
I mean, the basic idea is pretty simple. You use living organisms to check on the health of an environment. It's kind of like the old canary in a coal mine idea, but, much more scientific now.
Right, more sophisticated. And Apis mellifera, the honeybee we all know,
Yeah.
they turn out to be really good at this.
Fantastic, actually. Their honey, their pollen, they're already pretty well-established biomonitors, especially for trace elements like metals.
Why honey specifically?
Well, honey is particularly great because, first off, it's everywhere. You find beekeeping in cities, suburbs, rural areas, pretty much globally.
Uh-huh.
But the real key is the bees' behavior. When they're out foraging for nectar and pollen, they're interacting with, everything in their little world, within about a 3-square-kilometer radius of the hive, usually.
So the air, water, plants?
Air, water, plants, the soil, even tiny dust particles floating around. They're constantly sampling their environment.
And they bring all that back to the hive.
Exactly. And tiny bits of that environmental material get incorporated right into the honey itself. So the honey ends up being this perfect little time capsule, a passive sample of what was going on locally while the bees were busy.
Wow. And we've seen this work before, haven't we? Like
Yeah.
in really specific situations.
Oh, definitely. The famous example is after the Notre Dame Cathedral fire in Paris back in 2019. Honey collected nearby clearly showed that sharp spike in atmospheric lead pollution from the fire. It really captures those acute events.
Okay, which brings us neatly to the main event in this paper, the COVID-19 anthropause. You mentioned this unique window in 2020. Lockdowns, restrictions, just a massive slowdown in normal human activity.
Yeah, traffic, industry, travel, so much was curtailed. Awful time for people, obviously, but it accidentally created this huge, unplanned, natural experiment for environmental scientists.
A chance to see what happens when you suddenly turn down the dial on human pollution sources.
Precisely. An unparalleled opportunity to see how quickly or even how our environment reacts when those anthropogenic, human-caused pollution sources are suddenly reduced or shifted around.
And the impact wasn't the same everywhere, right? Restrictions varied a lot.
Hugely, which is why this study focused on two really different cities. The Brussels Capital Region, or BCR, in Belgium, and the Metro Vancouver Regional District, MVRD, in Canada.
Okay, so same global pause, but applied to two very different urban stages.
Exactly right. Brussels is, ancient compared to Vancouver. Urbanized since the first century, very dense core, then density drops off. Vancouver is much younger, mostly developed in the last 150 years, much more sprawling in its layout.
And those differences matter for pollution.
Oh, definitely. The age, the density, the structure, they all influence how pollution patterns form and, crucially, how they might change when activity shifts.
So how did they actually use the honey to capture the anthropause effect in these places?
Okay, so they collected honey samples from hives located in urban, suburban, and rural areas within both regions.
Right.
For Brussels, they had samples from 2019, so before, and then again from 2020, during the main restrictions. For Vancouver, they compared honey from 2020 to a historical data set they had, collected between 2014 and 2019. That acted as their baseline before picture.
And they looked at dust, too.
In Brussels, yeah, they collected some dust samples as well, just for another comparison point.
And what were they actually measuring in the honey?
Two main things. First, the concentrations of 16 different metals, things like aluminium, cadmium, copper, iron, lead, zinc, a whole suite.
Okay.
And second, really crucially, they measured the isotope ratios of lead.
The fingerprint part you mentioned. telling you where it came from.
Exactly. Lead isotopes have different ratios, different sort of flavors depending on their origin. Is it from a specific type of rock, a particular industrial process, or is it legacy stuff like leftover lead from old gasoline emissions?
Got it. So concentration is how much? Isotopes are more about the source.
You've got it. Concentration tells you the amount isotopes give clues about the origin.
And the lab techniques they used. Pretty standard stuff for this kind of environmental chemistry.
Yep, standard, but, high precision. They used microwave acid digestion to prepare the samples. Then things like ICP-MS, that's inductively coupled plasma mass spectrometry. Fancy name. But it's the tool you use to get really accurate measurements of metal levels and isotope ratios.
Okay, now before we jump into the results, the paper mentions the metal levels themselves. Was the honey dangerous to eat?
That's a really important point they made sure to address. And no, for the vast, vast majority of samples, the metal concentrations were well within international safety limits for honey.
Like the WHO limits?
Exactly, like the WHO FAO limit for lead, which is 0.1 micrograms per gram. Only one single urban sample in Brussels was just slightly over that. So the key takeaway there is, while honey is a fantastic environmental indicator, these results didn't suggest widespread health risks from actually eating the local honey in Brussels or Vancouver.
Okay, good to clarify. Right then, the findings. The paper calls it a tale of two cities and their suburbs.
Yeah.
That definitely sets the scene for some differences.
Oh, absolutely. Things played out very differently. Metal levels in cities are usually tied pretty closely to human traffic, industry, just people living. You'd normally expect the highest levels downtown. But the anthropause really scrambled that picture in some unexpected ways.
Let's start with Brussels then. What did the bees tell us there during the 2020 restrictions?
Okay, this is where it gets really interesting and honestly a bit counterintuitive at first glance. In Brussels, the honey showed significant increases in 9 metals: aluminium, cadmium, chromium, copper, iron, nickel, lead, titanium, and vanadium.
Yeah.
Yes, increases. But here's the kicker. It wasn't in the city center. These increases were specifically found in the suburban sites in 2020 compared to 2019.
Wait, increases in the suburbs during a lockdown? That seems backwards. Shouldn't things have gotten cleaner?
Right, that's the initial thought. But the researchers proposed a really plausible explanation. During the strictest lockdowns, people weren't commuting downtown, sure, but they also weren't traveling out of the city region for holidays or long trips. They were staying put.
Mostly at home.
Mostly at home, and for a lot of people in Brussels, home is in the suburbs. So the thinking is this likely led to more local traffic within suburban areas, short trips for essentials, maybe, plus potentially increased residential energy use, heating, cooking, everything you do in your home 24/7, all contributing to local emissions right there in the suburbs.
Okay. So the pollution didn't disappear, it just shifted. It became more concentrated or intense where people were actually spending all their time.
That seems to be the most likely explanation. It really highlights how dynamic that link is between where people physically are and where pollution shows up. Another interesting thing in Brussels, before COVID, that classic pollution gradient, urban highest, then suburban, then rural lowest, wasn't actually that clear for many metals. But during the restrictions in 2020, that pattern actually became clearer for some metals like copper, iron, lead, titanium, and vanadium. It was almost like the pause removed some of the background noise from people moving all over the place and let the underlying urban, suburban, rural differences show through more strongly for certain pollutants.
Fascinating. What about other metals in Brussels? Anything else stand out?
Well, they noted some increases in barium, cobalt, and manganese, specifically in the rural sites, which they linked more to agricultural activities like fertilizers or pesticides, perhaps. They also looked at correlations between metals. Some, like iron, molybdenum, antimony, titanium, vanadium, were strongly correlated with lead, suggesting they share common sources, probably traffic and industry.
And others weren't correlated.
Right. Others showed no strong correlation, which points towards different, more widespread sources, maybe including that increased residential activity we were just talking about in the suburbs, less of a single point source, more diffuse.
Okay, so Brussels suburbs saw unexpected increases, likely due to activity shifting outwards. Now, let's cross the Atlantic to Vancouver. Was it the same story or totally different?
Mostly different, actually, particularly in the suburbs. In Metro Vancouver, the honey from suburban sites showed pretty much what you would expect. Significant decreases in several metals: chromium, lead, antimony, titanium, and vanadium during the 2020 restrictions.
And those are traffic metals.
Yep. heavily linked to traffic. Things like emissions, brake wear, tire dust, general road grime kicked up by vehicles.
Right.
So less commuting, less driving around the suburbs meant less of that specific pollution. The bees picked it up loud and clear.
Okay, that makes perfect sense. Vancouver's suburbs got cleaner, at least for those metals.
Exactly. But just like Brussels had its surprise, so did Vancouver, only this time it was in the urban areas.
Oh, what happened downtown?
Well, despite the expected drop in downtown traffic, the honey from urban Vancouver sites actually showed relatively higher concentrations for 11 different metals in 2020 compared to the historical baseline data.
Higher, not lower.
Relatively higher, yeah. Now, it wasn't a statistically significant increase across the board for all metals in the urban zone, but it definitely wasn't the clear decrease they saw in the suburbs. And certainly not what you might initially predict just thinking about fewer cars downtown.
Okay, why would urban pollution stay relatively high if traffic was down?
The study points to a couple of key factors. One might be what they call the lockdown rebound effect. Even if overall traffic was lower, maybe more people in the city center who did need to go out chose to use their personal cars instead of public transit, keeping localized traffic still a factor.
Okay, that's plausible.
The other, and possibly bigger influence, especially for Vancouver, is major non-traffic pollution sources that didn't shut down. Vancouver is a huge port city.
Right, the Port of Vancouver.
And the port remained very active throughout 2020. In fact, activity apparently even increased slightly by the end of the year compared to 2019. Shipping is a known source of various metal emissions. So that constant activity from the port could have easily counteracted or masked any reductions from less road traffic in the nearby urban areas.
Ah, so the port acted like a baseline source that kept pumping out emissions, keeping those urban honey levels relatively high, even with fewer cars.
That seems to be the strong suggestion. It really shows how urban air quality is this complex mix. You cut back one source, like traffic, but if other big sources, like shipping or industry, keep going, the overall picture might not change as much as you'd think.
So the urban-suburban-rural pattern in Vancouver?
It's still held in 2020 urban, generally highest, rural lowest. But the difference was less pronounced than historically, mainly because those suburban levels dropped significantly while the urban levels kind of stayed put. They also noted the usual influences, road dust, maybe some fuel combustion signals, agricultural stuff in rural areas. Similar factors to Brussels, but that urban-suburban contrast during the pause was the really striking Vancouver story.
It's just amazing how the same event, the anthropause, triggered such different responses in the local environment, all captured by bees.
Mm-hmm.
Okay, let's bring in those lead isotopes, again, the source fingerprints. How do they add to the story?
Right, the isotopes. This layer gives us clues about where the lead pollution was coming from, not just how much was there.
So differentiating between, say, lead from car brakes versus maybe legacy industrial pollution or even natural rocks.
Exactly that. It adds that crucial dimension of source attribution. And, surprise, surprise, Brussels and Vancouver showed different patterns here, too.
Okay, what did the isotopes reveal about Brussels' lead sources?
In Brussels, the lead isotope ratios in the honey, they varied a bit, but there were no clear spatial trends. You couldn't really distinguish between urban, suburban, or rural sites based on their lead isotope signature.
No pattern.
Not really. The isotope values they found overlapped with known signatures from historical European lead sources, like old leaded gasoline, but also with local geological sources. There are old zinc lead ore deposits nearby, and they matched the dust samples they collected too.
What does that lack of a clear pattern suggest then? A big mix?
Pretty much. It suggests a fairly well-mixed or homogenized distribution of lead sources across the whole Brussels region, probably a legacy of its long, dense history of urbanization and industry. You've got this widespread background legacy lead signature mixed in with more current emissions.
So for Brussels, the amount changed, but the flavor stayed the same.
That's a good way to put it. The study concluded that for Brussels, looking at the metal concentrations was actually more informative for seeing the anthropause effect. The sources of lead didn't fundamentally change during the lockdown. The amount coming from those sources fluctuated, especially in the suburbs, but the overall isotopic fingerprints stayed pretty consistent across the region.
Okay, Brussels lead.
Hmm.
A well-stirred historical pot.
How did Vancouver's isotopes compare? Did they show more of a pattern?
They did. Vancouver's isotopes told a much clearer spatial story, and they revealed a really subtle but significant effect of the anthropause, particularly out in the rural areas.
How so?
Well, even before COVID, Vancouver showed a trend. Urban honey tended to have lead isotope signatures closer to known anthropogenic sources, like road dust. Rural honey, on the other hand, had signatures that were more radiogenic, meaning closer to the natural background lead found in the local geology.
Okay, a baseline difference. And what happened during the 2020 restrictions? This was a really neat finding. During the restrictions, the honey collected from those rural sites showed a distinct shift towards even more radiogenic lead isotope ratios. Their signature became even closer to the natural background geological lead signature for that area.
Why would that happen? Why would the rural honey get more natural during the lockdown?
The interpretation is pretty cool. In these rural areas, the amount of human-caused lead pollution is already pretty low compared to the city or suburbs. So the idea is even the modest reduction in things like traffic emissions drifting out from the city during the anthropause was enough to subtly change the overall lead mix in the air.
It let the natural signal come through more strongly.
Exactly. The reduction in the anthropogenic noise allowed that underlying natural geological fingerprint to become relatively more prominent, more detectable in the honey samples via the isotope analysis. It really demonstrates the sensitivity of honey as a biomonitor. When background pollution levels are low, it can potentially pick up even quite subtle shifts in the sources of pollution.
So the honey isn't just measuring how much, but it's sensitive enough, especially in cleaner areas, to hint at shifts in where the pollution is coming from, too.
That's exactly what the Vancouver rural isotope data seems to show here. It highlights why looking at both concentration and isotopes gives you such a richer, more complete picture of what's happening in the urban environment.
Okay, this has been, well, quite a journey through Brussels and Vancouver, all guided by honeybees. Let's try and pull it all together. What are the main takeaways here about honey, cities, and this big disruption?
I think the absolute core message is that honey worked. It successfully captured these really complex and definitely non-uniform shifts in atmospheric metal pollution during the COVID restrictions. It completely validated its usefulness as a sensitive biomonitor, even for tracking sudden, large-scale environmental changes.
And the fact that the two cities responded so differently is key.
Absolutely crucial. You had Brussels suburbs showing those unexpected increases, suggesting human activity patterns physically shifted within the region. Then you had Vancouver suburbs showing the expected decreases from less traffic, while urban Vancouver levels stayed relatively stable, likely due to that lockdown rebound effect and persistent sources like the port.
And the isotopes added that whole other layer about the where from.
Right, showing that more homogenized, mixed-source landscape in Brussels, where concentration changes told the main story, versus Vancouver's cleaner rural zones, where the isotopes were sensitive enough to reveal that subtle shift back towards natural background sources when the human contribution dipped. It just underlines the complexity, you know? Urban pollution isn't simple. It's tied to the specific mix of activities and the structure of each city.
Now, the paper did mention some limitations, didn't it? Things to keep in mind.
Yeah, a couple of important ones. Honey collection is seasonal, right? Bees make honey mainly in spring and summer. So the study really only captures a snapshot during that production circuit each year. It doesn't tell you about winter, for example.
Yeah.
And also, comparing land use categories like urban, suburban, rural can be tricky between cities as different as Brussels and Vancouver. Definitions vary, structures vary. That's why they were careful to analyze them as two separate case studies rather than trying to make direct statistical comparisons between the two cities themselves.
Right, makes sense. So given all that, why does this research really matter to us, listening now? What's the bigger picture here?
Well, I think this kind of study is incredibly relevant for, the future of cities. Our urban areas are constantly changing, growing, dealing with climate change, facing new challenges. Understanding how they respond geochemically to sudden, major shocks like the anthropause gives us really crucial insights.
Insights for planning.
Exactly. For urban planning, for developing smarter environmental policies, for guiding sustainable development. Knowing how the system reacts helps you manage it better.
And the potential for using honeybees or similar biomonitors more widely in the future seems pretty significant too.
It really does. Imagine setting up long-term honey monitoring networks in and around cities. It could be an invaluable, relatively low-cost way to track environmental trends over time, not just react to sudden events. The study also mentioned the need for proper archiving of honey samples so we can go back and reanalyze them later, and for developing standardized honey reference materials. That would help researchers everywhere compare their results more reliably.
So there you have it. We've really seen how these tiny, incredibly industrious allies, the honeybees, have given us this unique, complex, sometimes unexpected picture of how two very different cities responded chemically during that unprecedented global pause.
It's just such a powerful reminder that honey is way more than just something sweet for your toast. It's this incredibly sensitive messenger of environmental change. It offers this deep, localized look into the really dynamic relationship between what we humans do and the chemistry of the places we live.
Yeah, absolutely. And considering how clearly these urban systems, tracked by honey, reacted to that huge, sudden change in human behavior, it really makes you wonder, doesn't it? What about the more subtle, ongoing shifts in our daily lives right now? How we commute, where we choose to live, what we consume. Could those be quietly reshaping the geochemical landscape of our cities too, maybe in ways we don't even notice yet?
That's a great question to ponder.
Definitely something to think about until our next deep dive.